Hello, my name is Raul-Martin Rebane. I'm from Cybernetica, and I'm here to talk to you what's new in ZK-SecreC. So ZK-SecreC is a domain specific language, and the first slide is always to justify our existence, right? So why did we make a new DSL? And we entered into a DARPA project called Civ with our friends from Ligero and Galois. And in that project, we wanted to make zero-knowledge proofs, which are in environments where zero-knowledge proofs currently are not. So we wanted to aim for big circuit sizes and more complex problems. And so what we wanted to capture with our language was that in a zero-knowledge proof, you have these two dimensions for information. One is the domain. So for example, it's not just that the value could be public or private. It's that a value could be private only for the prover. It could be private such that only the prover and the verifier can see it. Or it could be fully public, in which it is known during compile time. Another quirk of zero knowledge is that we have on-circuit and off-circuit computation. So anything that is actually executed within the proof versus stuff that the prover could do like in their head. And we took these notions and we built the type system from them. So for each variable, like on the right you see x is int pre-prover, we have this kind of triple where one is the unqualified type, and then we have what stage it is and what domain it is. So for example, x pre-prover is x being int pre-prover means that it is off circuit and visible to the prover only. The slide switcher is currently not operating. I think the cursor may have been moved. Thank you. You can also classify, so there's like a ordering between these values. So for example, something that is in the public domain can be brought to the prover domain, but it cannot go in the other direction. And similarly, anything that is on the protocol, so like that is on circuit, can be also brought off circuit. So like obviously if you know the value, so you take it off circuit and then you do some computation with it, and then you can do some witness expansion with it, where we allow new wires to be created with this wire operator, which allows you to move from pre to post. And then obviously, as it is a new input to the circuit, typically it involves some checks as well. So this differs a bit from the other languages, which typically have like a public-private type. But those tend to conflate two things, either to conflate the prover and the verifier, in which case certain checks cannot be automated exactly. For example, if I have some process in which I'm loading in integers, and I wouldn't trust the prover to correctly hand them into me, so I might run some checks when the prover applies these integers, but not when the verifier does. This cannot be done if we do not differentiate between prover and verifier. Similarly, verifier and public can be conflated, in which case for example, with like public, we can know what is known during compile time, and then we can do some certain optimizations, which we can't if we just assume that it's a verifier input. And well, this type system might seem complex at first glance, but to be frank, so is zero-knowledge programming. We have taken the approach that, given the difficulties in zero-knowledge programming, we shouldn't have to shy away from some of the intricacies that zero knowledge brings us, because any programmer writing a zero knowledge program already needs to keep track of in their mind, for example, any constraints, because unqualified circuits are really, really dangerous, and that is something that only a programmer can know if they've written incorrectly. Like if I'm using some clever workaround to get using my specific that only works on this specific field, that I can drop these constraints, that is something that the compiler cannot know, or well, we're not there yet at least. And so that is something that only the programmer can know, and there is a lot of responsibility on the programmer to get it right. Similarly, zero knowledge currently is at a state where to get high performance, you need to optimize a lot. We have seen this in our examples where if you write the program naively versus when you use witness expansion and other tricks, you will get orders of magnitude of performance increase. So that is again like an argument for the program is already assumed to be quite. There is already zero knowledge required from the programmer, so why not make it explicit? And some of the difficulties of this kind of larger type system can also be hidden away quite easily from the programmer by using polymorphism and inference. So in this case, we have polymorphism over the field, the stage, and the domain. So this function sums a list, and the input on the left here in the brackets, you see that n is some natural. You have $S that is any domain, or just a generic domain, and at d is a generic, $S is a generic stage, and at d is a generic domain. So this takes in a list of integers that are uint of n, so that is like field elements of n, and of the generic stage and domain, and returns the sum, which is also in the generic stage and domain. So the advantage of this is that we can do interleaving, where we can interleave on and off circuit computation quite easily. This is something that is very desired for more complex programs. We've seen this, we've seen off-circuit computation things be also implemented in other languages like Noir, but I believe for them you can only define a function to be executed off-circuit, but we allow a bit more control in here. We also allow Rust FFI, meaning that if you have a Rust function, then we allow you to call that Rust function directly without any, we don't even do any transpiling or anything. It will directly call the Rust function. The only thing is that you have to conform to our types.
What is FFI?
Foreign function interface, so that you can call functions from other languages without issue. The cost of this is that we've had to build an effect system where, for example, when you're branching off, when you're doing conditional branching, like an if statement, based on a off-circuit value, and that will that creates a wire in one branch but not the other. That shouldn't be allowed, because that can reveal the value of the condition, like whether the shape of the circuit will then tell you what the value was. And so that is not allowed, and for that we have the effect system. So now I'll quickly show an example of what we've done with our language, because we in parallel built the language and also built the use cases to use it. So the motivation for this use case is that in Estonia there was a electrical vehicle subsidy, which had some terms in it where you had to drive at least 80,000 kilometers in Estonia within 4 years, and 80% of it had to be within Estonia. So it Couldn't be that you just get the subsidy and then drive around in Finland the entire time. The way that this was done in practice was using odometers, but this does not allow the user to see their input data for the verification. So for example, if they believe that they have complied with the conditions, but the system gives them an error or like a lower number than they imagined, then they have no recourse. In our case, we will have the full list of coordinates, and then they can argue their claim much better. So we built this demonstrator for the ARPA, and then this is the overall setup where we have this GPS tracker, so it receives coordinates to the car. The car logs the coordinates and signs them, and then the user will be able to download the coordinates from the car to their phone, and then on the phone itself run the zero-knowledge proof with the verifying server. In this case, it says Arlington because we did it for a specific event there, but the principle is the same. And one thing that is really cool here is that we got our runtime and integration with the mac and cheese protocol from Galois to work entirely within the phone. So they would download the coordinates and then execute everything on the phone using the phone as the prover. And this is the performance that we got. So assuming 1 hour a day driving, which is the US average as I looked it up, and 1 coordinate per 30 seconds, which is again standard for fleet tracking GPS. We got that for 1 month's worth of coordinates on the phone. It took about 127 seconds. And then with Pi 5, we got much better results because of hardware AES. Now, when we had this use case built out, we wrote it using mac and cheese backend in mind. So we used Mersenne 61 as the prime. We used some extra features like ARIA inequalities to speed up our inequality checks. And to do that, we also used the verifier challenges. So that's like an extra thing that the protocol is providing us, that they have the capability to give us verifier challenges. But this is not always the case. So for example, when Lehero asked us to provide the use case for them as well, they required a different field. So one that was fast Fourier transform friendly. And as far as I know, they did not have verifier side challenges. So to do this, it was actually quite simple. Because everything is polymorphic over the field elements, changing the field only required us to change one line and then recreate the Poseidon parameters. And then we'll double check that some constraints are okay, but it took very little time. With verifiers challenges, those are a bit more complicated, and that is a topic that we wanted to truly tackle on because we want to support many protocols. There is always going to be a mix of feature sets. So we wanted to truly support all of the backends, and to do that we had to add conditional compiling. So we added the type predicates for the features that we support. So currently we have field switching, verifiers challenges, function gates, and vectorization. And the usage of those requires a type predicate, and when you're compiling, you are compiling for a specific platform or protocol, and that performs the check of like, okay, this thing that you're trying to do, does your backend actually support it? And if not, you can branch on that condition and maybe run a different version of the same thing. So what we had was that we had our inequalities were all patched to execute at the end. And in that, we had already built it so that if the verifier does, or if the backend does support the verifier challenges, we run the inequality checks in one way and otherwise another way. So in truth, creating the output for the hero only took us about like a few hours of work, and then everything was okay. So that's like the simplicity of being able to swap the protocols if you have built out the hardware for it. The circuit, the backends that we currently support are the CivIR, like the textual interface. Now we've also added CircOm. We also support the VLE-based like MCK, mac and cheese, and we've also added ZKB++ as well, like recently. We're adding to that list this year. What we're adding, we're not entirely sure yet. And the feature set, yes, is like varied right now. So all of these things under Gallo and mac and cheese, those have been the things we've been able to achieve with them. Other things we have as well is that we have built out our standard library as we build these use cases. We have quite a lot of parsing work. We have the begins so that you can do ECDSA no matter what your actual field of the protocol is. All of those things we've built out over time. We do want to make it so that we don't have to reinvent the wheel as much. So for that, we have the FFI for Rust, and we're also adding CircOm imports so that if you have something already built out in CircOm, you will be able to just import those into ZK-SecreC directly and call your CircOm from ZK-SecreC. We have other use case examples as well. So now that our project is finished, we are able to switch over to open source. You can see the link to the GitHub there, and yeah, we have those also work as code examples for people to see how the ZK-SecreC actually works. And that is everything from me. Thank you. There's a gentleman there.
Okay. Wait. Just, we want everybody to hear you.
It's not that. What I'm saying is not important. That's what I was going to say. What's actually prevents you from doing something like people have built sort of ZK DSLs in Rust. What is actually the limit doing, like using, like just kind of encoding all of this in the Rust type system and then using other compiler layers that somehow is a bit more open that way?
I see. One thing is that like our backend integrations are also important, right? So also any sort of optimizations that we can perform, and yes. So for example, with function gates, we have an annotation where you can say that, well, this should be converted entirely to a subprocess in the circuit, and I think that is something which I'm not gonna. I don't know if I can claim that you cannot do it, but like it's a reason why we did it.
More questions? Yeah, I wanted to ask, so you had this nice example with the car taking GPS coordinates, right? So who signs like the coordinates?
The coordinates in that case, well, the cursor I think is again in the corner. I cannot move my slides. But we need to establish a source of truth. In this case, we assume that there is a non-tamperable device in the car that only logs coordinates. Or it doesn't have to be non-tamperable, at least tamper evident, so that, well, if there is some tampering, we can know. So
the car signs them, right?
Yes.
In that device, and then it transfers to the mobile device.
Exactly.
It doesn't do the proving.
It does not do the proving.
Yeah, okay.
With the Pi 5, we did ask, like, okay, what if it did do the proving? Because that is a device we use for logging. And but just in general, we wanted to put as few assumptions as possible into the setup. We felt that well, you need to get the trusted coordinates somehow, and that seemed the direction.
Yeah.
There is a question from the gentleman behind you.
Yeah, thank you for your presentation. I'm just wondering what the performance of your approach. So if we are comparing the circuit size from the manually optimized circuit, for instance, like if we are comparing the circuit from your tool and like ArcWorks library, so what's the performance of the circuit size? And also, is there any way to embed or include the outside optimized circuit in your specification?
I do not have these kinds of comparative performance metrics. To your other question, yes, we are adding the circum imports, if that answers your question. But yes, we do want to make it so that the users are able to import circuits that are already pre-optimized. We do currently include Bristol fashion circuits as well from the MPC realm. So those are already integrated. Where if you have, that is actually what we use for SHA-256 as well. We didn't want to implement that ourselves. So yes, for those really optimized circuits, you can directly import.
Okay, let's thank Raul again.
Thank you.